Okay, so our next speaker is myself. I'm Jason Bramburger. I'm at the University of Victoria right now. I'm very excited to share with you some work that I've been doing with a few members of the University of Washington, both the physics and the applied math department. And we've titled this Sparse Identification of Slow Timescale Dynamics. So I want to begin with just a simple sort of personal anecdote that will give us all an idea for the types of dynamics that I'm going to be interested in today. So when I was living in Victoria, I lived about 2 blocks from the ocean, and each night around the same time, I would go for a walk on the beach, and I would mentally take note of how high the tide was. And if I was really, keen, I would think back to the day before, and I would remember that the tide was almost at exactly the same height. But if I was really, really clever, I could remember that maybe about a month ago or so, the tide was at a radically different height. And so luckily for me, this has been well documented. And it turns out that tides evolve on these very distinct multiple time scales. So what most of us know, for example, is that in about a period of 1 day, a tide goes through 2 high tide and 2 low tide phases. But if you start marking the height of the tide and you look on longer time scales, so for example, as you can see on the left-hand side here, this is from just outside of Seattle, which was very close to me. When you look over a period of, say, a month or a year, you have this very complex emergent slow timescale behavior that's coming through, right? So you have this fast periodic behavior or almost periodic behavior on about a 1-day time frame. But then when you start looking at longer timescales, you have this extremely complex and what could potentially be described as chaotic motion that is governed by stronger gravitational influences than just the moon. And another place where you would find something similar to this with these multi-scale dynamics is in the motion of the planets around the sun in our solar system. So if you think back to your middle school science class, we can all probably regurgitate the fact that the planets move around the sun in an almost perfectly elliptical orbit. But if you start simulating the solar system for millions of years into the future, what you find is that, yeah, this is the case on on short time scales, so on the order of years. But when you start looking at the dynamics of those planets on, say, thousands of years or tens of thousands of years, you find that there's, again, a slow drift, which can only be found when you start looking on these very, very long time scales. Now, in the case of planetary dynamics, this is referred to as the eccentricity of the orbit. It's a sort of slow wobble that comes off of these almost perfectly elliptical orbits that we know so well and that we think of. Now, when it comes to actual dynamical systems and differential equations, we have a pretty good way of handling these types of multi-scale systems. So for example, imagine that you're given an ordinary differential equation that takes the form of what you can see in the top right of my slide here. You can see that this is a non-autonomous system. You have some small parameter epsilon. This is your scale disparity parameter. And you can see by the assumptions that I put on here that the fast dynamics, the order t dynamics, are periodic. That's coming from the periodicity in your function f. But the presence of the epsilon out front here tells you that there's also a slow drift taking place. And that's coming on a slow time scale of order epsilon t. Now, in dynamical systems, we have what's referred to as averaging, which literally tells you that you can average out those fast timescale dynamics on the right-hand side of that ordinary differential equation, right? This is just an integral over one fast timescale. And what you're left with is a completely autonomous differential equation. I put it in the form of a variable y here. And now you can really see that this is evolving on the slow timescale, the epsilon t timescale. And what the theory of averaging really tells us, not only does it give us this average differential equation, but it tells us that the solution of the original differential equation x and the averaged equation y are within epsilon of each other. The error between these two things is on the order of epsilon on a very, very long time scale, on your epsilon t, your slow time scale. And so what you typically get is something that looks like the lower left-hand image here, where you can see the blue curve that represents your x of t. You can see these order epsilon wiggles that are coming in here. And once you average out those order epsilon wiggles, you get this red curve, which is really telling you that slow drifting dynamics. And I want us to really appreciate how great this is, right? Because this tells us, this process of averaging tells us exactly how the slow timescale dynamics behave. But this comes with a massive limitation. And that limitation is that we need a lot of information about a system if we want to apply averaging. The first limitation is that I have hardly encountered any systems in differential equations that are amenable to averaging, right? That actually look like this equation in the top right. Second of all, a lot of gathered data doesn't even come with an explicit differential equation. So what I want to talk about today is a way of sort of averaging if you're not given equations. How can you extract out these slow timescale dynamics, these averaged equations, so you can forecast these signals long into the future if you're not given an equation that governs their dynamics? And so the setting for what I want to talk about today is that you're given some time series, or what I'll refer to as a signal. And when you look at that, it looks like it should be able to be averaged. So what do I mean by it looks like it should be able to be averaged? I mean that there's clearly some periodic fast component here, right? It looks like my tidal dynamics. It looks like my planetary dynamics. But when I start zooming out, it becomes very clear to me that there is slow dynamics in here as well. And so what I want to be able to do is I want to coarse grain my signal. I want to track my signal, not continuously, but just after each fast period takes place. And then the goal will be to discover a mapping which iterates me along these coarse grained components of my signal, right? So find some mapping f so that f of xn is equal to xn plus 1. And what this little bit of calculus is showing you at the bottom of the board here is that if you can find this mapping f, a simple little Taylor series expansion tells you that the order epsilon terms in your mapping f are exactly the averaged equations which describe the slow timescale drift. I'll be referring to this as G as we go through. And so if you rearrange that equation on the right-hand side, that tells you that if you can find the mapping f, you can get back to the averaged equation, G, just by a simple rearranging of this equation, of this little Taylor expansion that I have at the bottom here, up to order epsilon squared. So there are two major components that are required to do this. The first of which is you need to know the fast timescale period. And the second of which is you need to discover that mapping f. So let me talk about the fast period first. The way that we're going to find the fast period is using very recent work due to Dilutsky, Tao, and Koots, published in Physical Review E this year, which they describe a method of extracting the fast frequency using dynamic mode decomposition. So in principle, dynamic mode decomposition is a fairly simple idea. And it says that if you are given some time series, you just want to fit the best linear model to that time series. So you want to find some differential equation, x dot is equal to ax, find that matrix A, and that will be your best fit. Now, if you bring this up to anybody in the mathematics community, they will say this is probably a terrible idea. And the reason for that is because you would expect your time series that you're given here to be highly nonlinear. And I couldn't agree more, right? This would be a very bad idea to apply this to the entire time series as a whole. But what the authors of this study actually tell you is don't do it for the whole signal. Take a small window of the signal, a subset of the signal, so that on that small subset, all you can see is the fast evolution, maybe 2, 3, 10 periods of the fast timescale dynamics. But inside of this window, you shouldn't be able to observe the slow dynamics, right? They should be approximately constant. And so what you do is on that little window, you apply the dynamic mode decomposition there. You find your linear matrix A. You extract the eigenvalues of that matrix A. We know that the eigenvalues that lie on the imaginary axis will be those that represent the frequencies of the fast oscillation in that window. When you do that, then you advance the window by one time step and repeat the process. And eventually you're going to sweep this entire window over the whole signal. And what you should get is something that looks like this picture in the bottom right, which gives you a sort of statistical picture of what the fast and slow frequencies look like over this entire signal. All right, so on the horizontal axis, I'm plotting the window number. And on the vertical axis, I'm plotting the eigenvalues of the resulting linear matrix. And you should get two distinct clusters in this picture. The first of which is bounded away from 0. This is in green in the picture. This corresponds to your fast frequency. That's your fast timescale dynamics. Whereas there should be a number of eigenvalues which cluster around 0, and they should correspond to your slow dynamics, because if you remember, the slow dynamics inside of each of the windows is approximately constant, right? That's your 0 eigenvalue. And so what you can use now is you can use a simple clustering algorithm to tell you where that fast frequency is clustering around, and therefore give you the period of your fast oscillation over these over this multiscale signal that you want to average. And once you have that fast frequency, you can start coarse graining this signal, right? You can start tracking the signal after each period of this fast frequency, and that will give you these discrete iterates that evolve along the fast or along the slow time scale now. And as I mentioned before, what you want to do is you want to discover some mapping F that will iterate you along these slow coarse-grained signals. And the way that you do this is very simple. You're going to set this up as a huge linear algebra problem. So you're going to think up all of the possible functions that F could look like. And you're going to aggregate those into a library, and you say, okay, I imagine that my function F, it belongs to the span of all of these library functions. So if you use that fact, and you use the fact that F will iterate you along these xn's, then you can set this up as a huge overdetermined linear algebra system where now your unknowns are just the coefficients in your span, right? I'm calling this my element here psi. And why is it that I say this thing is going to be overdetermined? Because this should certainly have more rows than it has columns, right? You want to feed it as much training data as humanly possible here. But that comes with a bit of a problem, right? If this thing is going to be overdetermined, then it's not necessarily going to have a unique solution, and it might not even have a solution at all. So you have to ask yourself, what does it mean for me to have a solution here? What is it that I really want to get out of this linear system? And we thought about this. Many other people have also thought about this. And the course that we decided to approach this from is we want the sparsest solution, right? We want the solution that uses the least amount of elements from your library. And the way that we do this is following what's called the SINDY method due to Brunton, Proctor, and Kutz. And they say, okay, to promote sparsity in this solution psi, what you're going to do is you're going to pick some value lambda. You're going to call that your sparsity parameter. And you will look at that overdetermined linear system from the previous slide, and you'll find the least squares solution. And then in your coefficients of your span, everything that is smaller in absolute value than lambda, get those elements out of the library. So for example, if you have a 10 to the minus 6 times x squared, it probably means that x squared shouldn't be in your library. And so once you reduce the dimension of this library, you repeat the process. And you can continue to iterate and bootstrap this method. And essentially what you're doing is you're approximating an NP-hard L0 optimization process, right? You're just getting rid of elements in your library that are not necessarily useful. And what we know about this sort of very simple method to promote sparsity is that it performs comparably to lasso, and it also has convergence guarantees. Now, I can anticipate a question that's going to come up because this comes up every time I talk about the SINDY method with people. And people like to point out that there are two major hyperparameters associated to this method. The first of which is your choice of sparsity parameter, right? What should I choose lambda to be? And it turns out in this particular application of the SINDY method, we have a pretty good answer for you. If you think back to my little Taylor expansion that I did a few slides ago, I said that if you want to obtain the averaged equation governed by the function g, you just need to expand the function f up to order epsilon squared. So that means that you want to get rid of the order epsilon squared terms on this or in these coefficients. So that means take lambda on the order of epsilon squared. So that certainly solves one piece of this. But then the next piece you might be asking me about is, okay, well, what should I include in my library then? And the answer to this is everything. Everything you could possibly think of, right? If you think that maybe a sine function might be a good thing to include in your library, then include it. Because the bigger the library, the better. You're gonna whittle that library down as this iterative procedure goes through. So why not start with the most amount of possibilities that you can? Okay, so this is an overview of the method. It's just a very quick and dirty overview, but let's see it applied to some simulated data. And so the system that I want to talk about is a three-body problem. It's a Jupiter-Saturn-Sun system. This is simulated, as I said, with a three-body problem. We use the actual masses of Saturn and Jupiter, and we use initial conditions coming from astronomical data. This is in an inertial frame of reference, so the sun always sits at the origin. The picture that I'm showing you is the orbits of these two planets around the sun on the order of millions and millions of years. We did this with a symplectic integrator. It's very, very accurate. And what you can see being traced down here, at least in the orbital plane that these planets belong to, is that you have that regular elliptical, or it looks like it's almost circular pattern around the sun, but you can see that there's a slight wobble in the dynamics coming from this very slow drifting, this eccentricity of the orbit as you're orbiting here. And that's just coming from the gravitational influence of Saturn and Jupiter as they get close and far apart. Now, you can apply the sliding window dynamic mode decomposition method to this, and you can find that the fast periods, the fast orbital periods of these two planets around the sun are given as on the board. And for those of you who are pretty into planetary dynamics, you'll notice that this is almost exactly what we observe, what astronomers are observing as well for these periods around the sun. What you can also do is you can apply the sliding window dynamic mode decomposition again and find that the orbital eccentricity is also periodic, and it evolves on a slow time scale, which is on the order of 46,800 years. So it's 4 orders of magnitude larger, or sorry, 3 orders of magnitude larger than the fast periods. And what we show in our work is that the scale separation, that epsilon that I've been referring to throughout, this is just given by the quotient of these fast and slow time scales, right? So we have an explicit value for these epsilons, although it's not necessarily necessary for proceeding here. But we do now have all the ingredients to apply this slow extraction method. And the first thing that we'll do is we'll apply it to the orbit of Jupiter. So again, just for simplicity, I'll leave myself in the orbital plane. So I want to forecast myself in, say, X and Y coordinates. And what you obtain is a mapping which is surprisingly simple. You get a linear mapping that comes out of this. And this on the first line here, that's my mapping F. I can use that rearranging through the Taylor series, and I can recover the slow dynamics, that's G, which we thought was very interesting that pops out of this because you get a conservative system without telling it to look for a conservative system. And what you can see here now is that the slow dynamics, everything is confined to an ellipse. You can do the same thing for the forecasting of Jupiter, for Saturn, and you get almost exactly the same thing, right? The slow dynamics, they're confined to ellipse. And what this tells you is that on a very, very long time scale, tens of thousands of years, the orbits of Jupiter and Saturn, they're confined to these tori, for which you have a very fast drift in one direction, that's an orbit around the sun, and a very, very slow drift in another direction, which is your orbital eccentricity, governed by these averaged equations up on the board. Okay, so let me just conclude with a discussion of some future work, right? So the first thing that we would like to be able to do is really layer this work. So for example, with the planetary dynamics, there are a number of even slower timescales which come through. And so we would like to be able to say, okay, let's pick out the first averaged equation. Once we have the first averaged equation, let's average that to get the even slower dynamics. And you can think of this sort of hierarchy of slow average dynamics coming through. Furthermore, something that's very possible in the analytic setting of differential equations is that we can average equations where the fast dynamics are not necessarily periodic, but say almost periodic. So the question is, how would we approach such a phenomena when we're given just the data here? But really what we're interested in moving forward is extending this to spatial temporal systems, right? Can we average over space, say, instead of time, or maybe average over both space and time at the same time? And based on my background in math, what really gets me excited about this idea is the application of this to spiral waves. So spiral waves are these steady spatial patterns that look like spirals. They rotate very, very fast around some center of rotation. But what we know is that in certain parameter regimes, these things will also experience a very slow drift. And what we would really like to do is average out that fast rotation in space and be able to just describe how these things are drifting throughout space. So this is all stuff that we're thinking about moving forward. So with that being said, thank you very much.
Thank you, Jason. We have a Q&A. We have a question from the audience. So okay. Dmitry Todorov is asking, is there a version of dynamic mode decomposition for greater than 2 timescales?
Yeah, so the answer to that is absolutely, right? So I actually used it to get the slow time scale, the slow period of the planetary dynamic example that I gave you. But that paper that I referred to by Dalutsky, Tao, and Kutz, they do layer this. They can continue just by taking longer or wider and wider windows. You can extract slower and slower dynamics out of these things. So I would highly recommend taking a look at that paper. I believe with the planetary example, they go down about 6 different timescales or something like that. So you can continue to pull out these frequencies as long as you have periodicity on every single one of these timescales. That's sort of the drawback to using the dynamic mode decomposition. And that's what motivated us to take a look at these averaged equations where you might have something that, say, chaotic on a longer timescale as opposed to periodic.